Okay, let's start. So, in the last class, we essentially saw how to deal with mismatch. The takeaway is this: if you have a threshold voltage mismatch, you model it as though the transistors have the same threshold, but the error in the threshold voltage can be modeled as a small signal gate voltage added. Same thing for the beta mismatch. And as I mentioned in practice, the threshold voltage mismatch is the dominant, mismatch factor. So we typically consider this. And with respect to op amps, mismatch results in two things. One, of course, it results in an offset directly. Second, we also saw that if we have a fully differential amplifier like this, if we apply a common mode excitation, if there is a mismatch in the two halves, the positive and the negative outputs might not be equal, although you apply a common mode excitation, which means even though you apply a common mode signal, if you take the difference, that will not be zero. So this is what we call as common mode to differential mode conversion, and this is again a problematic issue in fully differential amplifiers. And then we started to look at noise. So just to summarize a discussion on noise, uh, it turns out any element that dissipates energy generates thermal noise. And for resistor, although it's a noisy resistor, the way we model it is this: we assume that the resistor is noiseless. So let us say this is your noisy resistor. You do the same thing our parents do. We say that our resistor is noiseless. It is a nice noiseless resistor, but the noise is coming due to a hypothetical voltage source that is kind of put in series with that. And the part spectral density of this noise voltage source, single sided value, is 4 kT times R. Now, other way to model it is, instead of having a voltage source in series with a resistor, I will say that I can have a current source in parallel to that. So the value of the current is going to be the voltage by R. So the part spectral density of the noise current is basically 4 kT by R. Now, similarly, even for MOSFETs, MOSFETs generate thermal noise. The way to model noise in a MOSFET is similar. We assume that the MOSFET itself doesn't generate any noise, but the thermal noise is due to a hypothetical current source added in parallel to the MOSFET. And the part spectral density of this is 4 kT times gamma times the transconductance, where gamma is an empirical constant. It's roughly 2/3 for long channel. And just to remind, this is valid only in saturation, right? This is assuming that the transistor is in saturation, which is where we would be interested to bias the transistor. Now, in addition to this thermal noise, as I mentioned, we also have another source of noise called as flicker noise. So, flicker noise, the deal is the part spectral density is inversely proportional to frequency. Okay. So, in practice, if you take a MOSFET, it will have both the thermal noise and flicker noise. Okay. Now, as I mentioned, thermal noise is basically coming from thermodynamics, because we have thermal energy at non-zero temperature. Charges have random fluctuations, and that's what results in thermal noise. So thermal noise is something very fundamental. There is simply you can't do anything about it. Whereas flicker noise, its origin is not fundamental. It is because of imperfections in the manufacturing process. So there are ways to tackle them. But thermal noise, on the other hand, is fundamental. And then we saw that if you make some circuitry comprising of all transistors and resistors and stuff, right? And let us say you apply an input, and let us say you're trying to measure the output. So you might be interested in measuring, let us say, an open circuit output voltage, or maybe let us say you're interested in measuring the short circuit output current. Either of them is okay. Now, ideally, you will expect that you'll get the output only due to the applied input. But now we know that all the transistors and resistors will generate noise. So we can model all of that noise using noise current sources. So let us say you have multiple noise current sources inside the network. Again, this is way to model the noise of each element. It is not as though a current source is there sitting in the network. Right? It is just for convenience. So which means now you will have the output due to both the input and the noise. And the nice thing about noise is the input we are going to apply is going to be a small signal. Same is the case with these noise current sources. Noise is going to be very small. So although the circuit might be nonlinear because you are using transistors, for small signals, how can you approximate it as linear? So which means if I were to only find the effect of noise, I can use superposition. I'll assume that since I'm dealing only with noise, input is 0. And then I have so many noise current sources. So you can again use superposition. You take one noise current source at a time. Let us say the power spectral density of, I'll consider kth noise current source having a power spectral density of S ik of f. So to find the output power spectral density here, you find the transfer function from the kth noise current source to the output. The output power spectral density is input power spectral density times this transfer function square. You do this for all the noise sources in the network and sum it up. That will give you the total power spectral density at the output. So this is how we kind of compute the power spectral density in our circuits. Now again, just to remind you, remember that we started with the understanding that the circuit can be approximated as a linear circuit. So we can use superposition. If we can use superposition, in principle we should be able to write only, let us say, I out of t or I out as some alpha 1 times in1 plus alpha 2 times in2 and so on. Okay. Now I'm able to say that the power spectral density is sum of the individual power spectral densities because the noise sources here are uncorrelated. Okay. Because if you want to find the power spectral density of this, or let us say you want to find the power of this, you take and square this. Now only if the cross terms are 0, it becomes equal to the sum of the individual powers. Right? And the cross terms become 0 if the noise sources are uncorrelated and have 0 mean. So this is what happens in practice. The noise sources are uncorrelated. They would never have met each other in their lives before. So no need to worry. And also they are 0 mean noise sources. So which means if you have sum of them, the power of the sum is same as the sum of the individual powers. That's what I'm saying. So that's why, since we can write the power as sum of the individual powers, even the power spectral density is sum of the individual power spectral densities. So two assumptions are being made. One is the fact that the circuit is linear, that is helping you write this using superposition. Second assumption is the fact that the noise sources are uncorrelated and have 0 mean. So that helps you write the total power spectral density like this in one shot. And as we saw in the last class, in practice it is much more convenient to model the noise in the circuit using an input referred quantity. So just like how for resistors and MOSFET, we told that we modeled it like this. We took out the noise and then represented as equivalent voltage here. That's what we try to do. We now want to make sure that the network now can be assumed to be noiseless. But the actual noise contribution, we want to model it using a hypothetical voltage source here. So this is basically Vn in. This is what we have. But here the issue is the fact that in general, remember that here this is going to be where you will be applying the input Vin. Now you design the network, but you don't have any control on what is going to be the source resistance of the input voltage source. So it can be anything. So in general, this will have a source resistance Rs. Correct. So which means if I short the input, I just have Rs at the input. So I'll redraw this. If I make input 0, I'll have just Rs here. So which means here also I'll have the same Rs. So now you see that the input referred noise voltage that you have modeled is basically divided between the source resistance Rs and the input impedance of the network. So which means not all of this is going to excite the network. And if you have a limiting case where, let us say, let me copy this. So let us say I consider a scenario where my Rs is much greater than the input impedance, or in other words, I will say Rs tends to infinity. If Rs is infinity, this is open circuit. Now it appears as though this noise voltage will not result in any noise current, but that's not obviously the case, because here even if I make RS infinity, the noisy elements in the network will generate noise. So which means voltage source alone was not sufficient to capture the noise in this network. So that prompted us to introduce an additional element, which was the noise current source. So this is what we call as input referred noise current. Right? So here I'll have additional input referred noise current. So now you see that even if I make RS to be infinity, the voltage source, yes, it is not contributing, but this noise current will inject the energy and result in the required noise current. Similarly, if you consider the other extreme, yeah, so let me see if I can make some space here. If you consider another extreme where the source resistance is 0, so which means this is going to be shorted here. Now you see that this voltage source is going and sitting and exciting the network directly. So all the noise will be contributed only by this voltage source. This noise current will not, push flow into the network because it will completely flow to the voltage source. So which means if I have a case where RS is 0, you only have contribution due to the voltage source. On the other extreme, if I have RS to be infinitely large, you only have contribution due to the input referred noise current. This is all happening because in practice you don't have a control on what the value of RS is going to be. So to capture to model the noise in the network for all values of RS, you need to have both the voltage source and the current source in the network. So now in practice, if you want to find the input referred noise, voltage and current, so let us say you start to find the voltage. You first consider a scenario where the noise is coming only due to the voltage, and that happens for what value of RS? RS 0. So you consider this case where RS is 0. So in this original network, you make RS to be 0. You find the output power spectral density like this. You take one noise source at a time, find the transfer function, and then sum up all the power spectral densities like this. Now the same noise must be captured in this equivalent model. So here the only thing that is contributing to noise is this input referred voltage noise. So the output power spectral density will be power spectral density of this times the gain from the input voltage to the output. So you basically calculate the transfer function from, let us say, this noise voltage to the output. So you take this output and divide it by the gain square, that gives the voltage power spectral density. Similarly, if you want to find the noise current, you consider a scenario where the noise is coming only due to the current, and that happens if RS is infinity. So in that case, you sort of open this, do the same thing, you calculate the output noise, and then find the gain from this noise current to the output. The output power spectral density by the gain square gives the input referred noise current spectral density. And again, here I have considered the output to be a short circuit current, but you can as well say that my output of interest is open circuit voltage, and you will get the same results. So here a couple of points I wanted to make. So first observation. So here please note that VNN and INN, they are capturing the noise of the same network, right? If so, do you think they will be correlated or uncorrelated? They will have a very good correlation. So which means, let us say you have a scenario like this. You get some variable, let us say VNN plus some, I don't know, some alpha 1 times INN or something. Let's say some R1 times INN or something. If you want to find the power spectral density of this, you cannot say that it is basically SVNN of F plus R1 square times SINN of F. Okay. Plus you also need to have a cross term. You'll have a cross correlation of these two. So you have an additional term here. That's what it means. So second point, this. So here we already know that if, let us say, my RS is 0, I have noise only due to the voltage, right? So by extension, so here look at this scenario. If I say that my input impedance of the network is infinity, if let us say the looking in input impedance of my network is infinity, you think I'll need both voltage and the current, or one of them will be sufficient? Why voltage will be sufficient? Yeah. Now, if you see, earlier the issue was, if I draw this separately, I had the voltage and the current. You had an RS here, and you had an effective Zn of the network here, right? So earlier the issue was, if the voltage was there, this will get divided between both of them. So now if Zn is infinity, the entire voltage will drop across this. What about the current? Do you think current will flow here? Open circuit, so none of the current flows. So this again leads to the observation that if Zn is infinity, you only need voltage or current. Only voltage is sufficient to model the input referred noise. So if it is kind of confusing, look at examples and it will become very apparent. It's not very difficult. But this is something to have in mind. If the input impedance is infinity, you don't need to have the input referred noise current. Cool. So let's look at a few examples so that we get a hang of these calculations. So let's start with a simplistic circuit, a common source. This is your common source. I'll just draw the small signal equivalent. So the drain is grounded. I have RD here. I'm going to apply the input at the gate, tap the output from the drain. So which means at the input, in practice, I don't know what is the source resistance, so I'll have something like this, Vin and RS. Now again, if I'm interested only about the noise calculations, what can I do for Vin? I can make Vin to be 0, so Vin is short circuit. So now my goal is the following. I want to make sure that I'm able to capture the noise in the network. So first of all, let me redraw this. So first of all, tell me what is the input impedance of the network? Infinity. So do you think I need to find both voltage and current? So what is sufficient? Voltage is sufficient. But so which means if I actually go and try to calculate the current, what do you think the current will become equal to? It will come out of 0. So for the first calculation, we'll religiously calculate both voltage and current, convince ourselves that the current is actually 0. So let's start with finding voltage. For finding the input referred noise voltage, I should use RS to be 0. So which means I am going to make RS to be 0. So here, how many noise sources are there in the circuit? One. Which is the only one? Two are there. Both resistor and this one, transistor. So I can model both of them as an input referred noise current. I'll call this INRD. I'll call this INM. Again, remember the direction of the noise current sources are immaterial because it is a random quantity. But once you assume some sign, you stick to it so that you don't mess up the calculation. So now our goal is to make sure that we are able to model this noise using an input referred quantity. So which means I'm interested to do the following. I'm interested to model it so that I don't need to worry about the individual noise contributors here. I want to have an input referred noise voltage and current. So which means here I want to have a noise voltage and a noise current, VNN and INN. And technically here is where you'll be going and connecting your Vin and RS. And in this particular noise voltage calculation, both RS and Vin are 0. So I'm going to short this. So again, the job is simple. In the circuit here, you find what is the output noise part spectral density, and then find the gain from the input to the output, output quantity by the gain square gives the input quantity. That's all. Right? So here again, you can either find the noise in the output voltage, but in practice, in most circuits, it's easy to find the short circuit current. I'll define this as my output quantity, because finally I'm referring everything back to the input. Whether it's voltage or current will not make any difference. Now you can choose whether you want to find voltage or current depending on which will be easier. But here you will see current will be easier, because now can you directly tell me what is my I out? I have two current sources. What is I out? Sum of the two. So INM plus INRD. That's all. This way it becomes trivial to write. That's all. So which means if I were to find S I out of F, because these two noise currents are uncorrelated and have zero mean, I can write it as perspective density of the individual quantities. So this is 4 kT gamma times Gm for the transistor. For the resistor, what is the spectral density? Remember, this is a noise current for a resistor, so it's 4 kT by Rd. So now we have found the output quantity. Now our goal is to make sure the same noise is captured in this model, right? So here I have voltage and current. Which of the two will contribute noise here? Voltage. So current is sort of not needed. So here again I'm interested to find the short circuit current. So here if I were to find the current S I out of F, that will be the input quantity times the gain from the voltage here to the current here. What is the small signal gain from this voltage to the current here? How much is it? I mean, this is a gate voltage. I'm interested to find the short circuit current. How much is that? Yeah, I mean, minus plus doesn't matter, because that will depend on the sign of the input. Yeah, so the gain is how much? Magnitude of the gain is Gm, right? So which means this is going to be Gm square. Gain square, so negative doesn't matter. Is that okay? Is this clear? I mean, you are basically finding the short circuit Gm by shorting the current and applying the input here. That's basically Gm. Minus or plus depends on whether you choose this as plus or minus. But finally, you are only taking the squared of the gain, so the sign actually doesn't matter a lot. So now these two have to be equal. So my SVNN will be this quantity by Gm square, right? Again, same thing. The output quantity by the gain you compute gives the input quantity. That's all. So I can directly write SVNN of F as this quantity. So let me write it for the sake of completeness. If I divide by Gm square, I'll have 4 kT gamma by Gm plus 4 kT by Gm square Rd. Basically, I'm taking this term and dividing it by Gm square. So any questions on this so far? How did we get this? Okay, cool. So this is the input referred noise voltage. Now we already know if I compute the input referred noise current, how much should that be? Should be 0, but let's verify it. For finding the input referred noise current, what is the value of Rs I will use? I mean, here I use 0. So for finding the current, what value of Rs I will use? Infinity. So which means this is open. Here also it is open. Correct. So here once again you can find what is SI out of F. Let's not worry about that. Okay, you'll get something. I don't want to calculate that. But what is relevant is the gain we have here, right? So let me actually make some space. Good. So here, as you see, because I have opened Rs, this voltage source is floating, so that is not going to matter. So now I have a circuit like this. So this is shorted. This is what you are supposed to find. And here you have a current applied. So let us say this is IN in. So what do you think is the gain from the current IN in to I out? 0. Any other answer? 0, infinity, 1.1, 3.14. No? Okay, I mean, if infinity is very confusing, see, only way to resolve infinity confusion is assume that there is a finite input impedance. Okay, and then you find it and tend R into infinity. Simple. Now tell me what is the gate voltage here? In in times R in. So what is my I out then? I mean, forget about the sign for now. Magnitude of I out. GM times in times R in. So the gain is GM times R in. So if I tend R into infinity, gain goes to infinity. So the gain here is infinity. So here you will compute some path spectral density. Finally, you will divide it by the gain. So the gain is infinity. So the input referred noise current will be 0. Okay. So that's why we don't have to compute it next time. So if the input impedance is infinity, we can straight away say that the input referred noise current is 0. Okay, so now let's move on to a second example where maybe the input impedance is not infinity. There is a finite input impedance. For that, let's look at our common gate. So common gate, I'll have something like this. Again, I'm drawing only the small signal portion. So let's ignore R naught for simplicity. This is RD. So as usual for common gate, where is the input applied? You apply input at the source, tap the output from the. So which means in practice, you don't know what is the source resistance RS, so you'll have something like this. V in and RS. And again, since I'm interested only in the noise calculation, I'll make V in to be 0. So here, what is the input impedance? R naught is infinity. So what is the input impedance? 1 by GM. So input resistance is not infinity. So here you will have to find both voltage and current. So let's do that. Let's start with voltage. For finding the input referred voltage, what value of RS I use? What did we use here? 0. So again, you try to model the noise in the circuit, noise sources in the circuit. So I have two noise sources. One is the transistor, other is the drain resistor. And let us say I'm interested in finding the short circuit output current. So I'll call this as before INRD and IN. So here again it should be straightforward to say what is small signal I out. It is summation of the two noise current sources INM plus INRD. Once again, these are uncorrelated noise sources with 0 mean. So I out of F, the path spectral density of I out is, I can write it directly, 4 kT gamma GM plus 4 kT by R. So now I just have to find the gain from the input to the output. So let's do that. Let me take it here. So now I don't have to consider the individual noise sources. Because we know that we are going to model the noise using an input referred noise voltage and an input referred noise current. And here is where you go and apply the input with the source resistance RS and V in. And in this particular calculation, V in is also 0, RS is also 0. So the input side is completely shorted to ground. So here, which of the two will be contributing to noise, voltage or the current? Voltage, because yeah, it's not needed. Now tell me, what is the small signal gain from this voltage source Vn in to the small signal current I out? In terms of Vn in, how much is this? Hmm? Yeah, I mean, remember that what is the small signal VGS for the transistor? Minus Vn in. So the current flowing up is how much? Flowing up is plus GMVn. So this is basically GM times this. That's fine, because R0 is not there. You don't have to break your head. Is this clear? So which means if I were to find the input referred, this fellow, that is basically this term divided by GM square. I'll not write the full thing, that you can do just algebra. This is fine. Same thing as what we had before. So this is basically half the job, because we just computed the voltage. So what do we have to find next? Noise current. And for finding the noise current, what is the value of RS I should be using? Infinity. Very good. So this side is open. Similarly, here I am opening this. So here it is open circuit. Now tell me, what is the small signal current I out? Let's do one by one. What portion of this INRD flows to I out? I mean, what is the contribution of this current INRD to I out? 0. Why 0? Hmm? I mean, remember that entire thing will flow through this entire thing will flow here. Fine. So this is going to be I mean, remember, everything is small signal ground, correct? The same small signal ground here. Okay. So this is going to be INRD. Now what about this current? Yeah, I mean, from here, if this current is INM, what about this current? Same. So both these currents are same. So what is the current that is flowing out? So you have 0 due to the other thing, right? So that's all. So here S I out of F is, how much is it? What is the perspective density here? 4 kT upon RD. That's all. So to now find the input referred, any question? Ask something? I mean, think of it like this. I mean, it's all small signal ground finally, right? If I draw it this way, it will become apparent. So here I found the output quantity. So I just have to find the gain here. So here voltage source will not contribute. So what is the gain from this current to the output current? The entire current flows to the output. So the gain is 1. So the SIN in of F is basically whatever you calculated, SI out by 1 square. It's 4 kT. Yeah. So let's look at one more example. So here I'll consider a common source kind of structure. I'll just have a source resistor here. I'll call this Rx. So here is where the input is applied, here is where the output is taken. So again, as usual, the assumption is we are going to have a source resistance at the input side. And let us say this is RD. So here, what is the input impedance? Infinity. So if I try to find the current, what will that be? So that will be straight away 0. Just have to compute the voltage, and for finding the, again, for noise calculations, input can be made 0. And I'm trying to find the input referred noise voltage. So what is the value of RS I'll use? So if I redraw this, so I have the same thing. The input side is completely grounded. So we'll have RD, RX. So how many noise sources are here now? 3 of them. So let me label that. So this is going to be NRD, NRX, and then let's say I'll have this. So as usual, I want to model this using the input referred noise voltage. So let me draw that to the side so that we have it for reference. So at the input side, I'm going to have the input referred noise voltage. This is the current, and I'm going to short the input. So here we already know the current is not going to continue. So again, the idea is the same as before. Let's say I now consider the short circuit current as the output. Same I'll consider here. So let's start finding the output path spectral density. So let's start with simple. So what about the contribution of RD? I mean this current source. That completely flows. So let me write it here. I out, let me write. So due to the current source INRD, the entire current flows, no confusion. Then let's look at other things one by one. So this I'll basically remove it for now because this we have accounted for. And for now, let's ignore this. Consider only this current. So maybe I'll erase this also. Consider only this. So how much of this current will flow to the output? I have INRX. Will the entire current flow or half part of it flow? What fraction will flow? Again, let's ignore R naught for all transistors to simplify things. Yeah, what is the fraction that will flow? Yeah, what is the looking in resistance? This resistance is 1 by GM. So it's going to be a current division. So it's the resistor downside Rx by now the remaining thing is the MOSFET current. So let's do that. So this I have accounted for. The only thing pending is now the MOSFET current. So with MOSFET current, I mean it is not trivial because here it is kind of connected between two nodes. Unlike the earlier cases where one of them was actually grounded and that ground was no proper ground, right? So again, it's not difficult. You can use KCL and solve for it. But there is one trick I like to use. Yeah, very good point. IOT is also grounded, but you are interested in the current flowing through that. Correct. Whereas here, this was grounded. There is other one. We are not interested in the current flowing there, right? That made it simpler. So that's why this is a floating current source. I mean, it's not difficult. You can use KCL and do it. But what I like to do is the following. So let us say you have two nodes A and B. and you have a current source between them. Let us say current I. So let us say I split it as two current sources with the same current I. Same, nothing has changed. Now, what can you say about the intermediate node voltage x Vx? That is not defined. If it's not defined, I can define it to anything in the world. What can I define it to? I can make it 0. I mean, the idea is if I make this 0, then your job becomes simpler. This is grounded. Now think of the original circuit. In the original circuit, you are pulling out a current I from the node A. That is happening here. You are pushing in a current I into the node B. That is happening here. Right? This node should see a current source. This node should also see a current source. Perfectly accomplished. So we are once again using the fact that the intermediate node voltage is not defined. So I can define it to anything in the world. I will make it small signal ground. So now that, if you do this, make sure that you don't mess up the signs, right? It should be pointing in the same direction. If you put it the other side, it's completely gone. So now it will actually be easy. So let me actually demonstrate that and so show why that is easy here. So here the direction I assumed is the current that's direction I've assumed is downside. So what I'll do is this. I'll assume one current I and M like this, and other current now we split it into two current sources. Now the nice thing about this is, now you see that whatever was happening for the noise current of RD will happen for this current source. So how much of this current will flow to I out? Yeah, can you what is it with what polarity? You'll have minus I and M because direction is down. So current flowing this side is going to be negative. And this current is basically same as the noise current of Rx. So whatever you computed for the noise current of Rx, same thing will happen for this noise current source. So that makes it simpler. So you have plus I and M times the same factor Rx by we are not saying you should always do this. You can whichever way you are comfortable, please go on. But I like to do it this way because I don't have to sit and bug my head. So if you do it, sorry, what happened? Yeah, if you do it this way, just be wary of the polarities carefully, right? So these two should have the correct polarity. So now it is done. So let's actually quickly write the complete thing, or maybe I'll take it to next page. But what I did, is it clear? Any questions on this? Again, remember this all small signal calculations. This entire noise analysis business is just based on small signal calculations, nothing else. The only piece of information you have to remember is power spectral density of resistor is 4 kT by RD. For MOSFET is 4 kT gamma GM. You just remember these two, rest is all a cakewalk. So that's why I've been emphasizing on doing small signal calculations. You should understand if a current is injected here, what happens to that, and so on. So let's simplify this. So this is INRD plus INRX times GMRX by 1 plus GMRX. So this becomes plus INM by 1 plus GMRX. So I'm just simplifying it to make a point here. Okay. So which means SI out of F, it's 4 kT by RD plus 4 kT by Rx times GMRX by 1 plus GMRX whole square. This is 4 kT gamma GM by 1 plus GMRX whole square. I'm just writing this fully for making a point later, not very critical now. So let us say now we have computed this. So what is the next step to find the input referred noise voltage? I have to find the transfer function from the input referred noise voltage to the output. Yeah. So here is what I have. So this is VNN. I'm interested to find the current flowing here or in the other direction. So if I have to find the current flowing here, what is the first thing I should find? I should find the source voltage. I'll use this color. So again, R0 is infinity. I'm applying a small signal voltage at the gate. What is the corresponding voltage I'll have at the source? I mean, okay, same is a very idealistic scenario, but what is the actual ratio? I mean, when will this be exactly equal to the input voltage? When current flowing through it is 0, which means what should be the value of Rx then? If Rx is infinity, it should be 1, right? If not, it will be less than 1. So just by like logic, what will be the factor that should come? Rx by? No, that doesn't make dimensional sense, right? This is resistance, but here it's a constant. So Gm times. Again, same thing, right? This is again buffer put in negative feedback. So gain by 1 plus gain, A by 1 plus A, beta is 1. Yeah, so which means if I know Vs, what is my I out? Can you tell me? Sorry, in terms of Vs, how much is I out? No. I mean, if I know Vs, what is I out? It is Vs by R or? So this basically becomes minus Gm by 1 plus Gm Rx. Okay. I'll write it clearly. Directly write it. So this is going to be minus Vs by Rx. So this is minus VNN. So the gain is this factor Gm by 1 plus Gm Rx. So to find the input referred spectral density, I'll go and divide this by Gm by 1 plus Gm Rx whole square. Okay. That will give me yes VNN of f. Okay. Again, the final expression is not relevant. I'm just showing it once for making a point. Where was negative? This one. Okay, good question. So I mean, here I had minus INM and this. So if I take the path spectral density, so what do you think we should do? Do you think these two are correlated or uncorrelated? These two are 100% correlated. So you can't directly take the sum. You should simplify it. I simplify it. It's what I get. Okay, yeah, okay, fine. Negative. Yeah, fine. Yeah, sure. Yeah, so now tell me if I have a signal x of t, I have a power p. If I have minus x of t, what is the power? Why? No, it's not. It's nothing to do with real signal here. How do you calculate the power of a signal? 1 by t, whatever, and then integration of, yeah, I mean, yeah, x square of t, right? Yeah. So doesn't matter whether it's x or minus. I mean, whether it doesn't matter it's plus or negative, it's going to be same. So if I simplify this, I'll get first term, which is 4 kt by rd, second into something, I mean some big factor, plus this will be 4 kt times rx, last term will be 4 kt gamma by j. Okay. So again, remember this is due to the resistor rd, this is due to the resistor rx, and this is due to the MOSFET. So I would like to drive your attention to this factor. For MOSFET, it comes out as 4 kt gamma by G, right? So I just want to explain why that makes sense. So let us say you have a MOSFET. So how do we model the noise in the MOSFET here? We assume that we have a current source added, direction doesn't matter. Now again, let's say for example source is grounded, doesn't matter, but simplicity, let's assume source is grounded. I'm interested to model the noise here using an input referred quantity. So do you think I'll need both input referred noise voltage and noise current, or one is sufficient? Why? Sorry? The input impedance here is infinity, so I don't have to worry about the noise current. So in principle, I can say that this can be modeled using an input referred noise voltage. So what will be the value of the noise voltage in terms of the noise current? How will you find it? Let's say this is the circuit. How will you find it now? Okay, you can first, let's say, find the short circuit current here. Short circuit current is going to be INM. And then what you do? I mean, let us say here I find the noise is INM. So what do I do next to find the input referred quantity? I find the transfer function from this voltage. So here Rs is 0, this will be this, to the short circuit current. How much will that be? So what is VNN in terms of INN? So what will be the path spectral density of this? What is the path spectral density of the noise current? Gamma gm by gm square. So this will be 4 kt. So this is one observation to have or make in mind, that if your input impedance of the MOSFET is infinity, then you can model the noise current, noise in the MOSFET using one single voltage source at the gate, having a path spectral density of 4 kt gamma by gm. Here I consider a grounded source, but in the previous example the source was not grounded. It still turned out as 4 kt gamma times 4 kt gamma by gm. So which means this is a good thing, because now in the in the future, for modeling the noise of the MOSFET, you don't need to do this specifically. We can assume that I'll take the original circuit itself. Yeah, here itself I'll say the noise of the MOSFET can be modeled as a voltage source VNM, right? So which means what will be, I mean, if I were to find the overall input referred noise for the overall circuit, that will basically include this directly, because that's what you're trying to do. You're trying to refer all of the noise to an equivalent voltage source at the gate. For the MOSFET, the noise itself is modeled as an equivalent voltage source at the gate. So this will directly come and appear in your overall input referred noise voltage. So which means if the input is applied to the gate of a MOSFET like this, the noise contribution of that MOSFET to the overall input referred noise voltage is basically the noise voltage of the MOSFET itself. So we don't have to go and compute it, like this every time. And remember, this is true as long as the input impedance is infinity, and that is okay because we are ignoring the gate capacitance here. So at high frequencies this might not be really valid, but yeah, we don't deal with that in this course. So what I'm saying is, if we have a circuit and let us say input is given to a MOSFET, the noise of the MOSFET can be modeled as an input referred voltage like this. So which means the overall input referred, if you find the overall input referred noise for the entire circuit, the contribution of MOSFET will straight away add like this. And this will have a path spectral density of 4 kt gamma by g. And this is a nice thing because in all our circuits, input is given to a gate of a MOSFET. So which means for those transistors, we don't have to go and compute the noise contribution. You can straight away write that input MOSFET directly adds to the noise. Is this statement fine? So then let me want to make one other point. So let's consider another circuit. Let's consider cascode this time. So M1, M2. Assume that it's output side is open circuited for small signals. So this is small signal ground. Input is here. Output is here. So once again here, do you need both voltage and voltage and current to model the input referred noise, or what do you need? Input impedance is infinity, so only voltage is sufficient. So for finding the voltage, what do I do to the input side? Remember, I'm going to have an RS generally. For finding the voltage, I make RS to be 0, which means effectively input is shorted. So now tell me, what is the contribution of M1 to the overall input referred noise? Yeah, if I directly write it as Vn in of F, for the overall circuit, I'll directly have one term which is 4 kT gamma by Gm1. That is sorted. Now the only thing pending is for the cascode transistor M2. So let's do that. So again, the noise of M2 we can model as a current source or an equivalent voltage at the gate. That is, we can have a voltage source here or a current source. I'll use current source for this case. Or maybe I'll use a voltage source. I think that is simpler here. I'll assume that it's a voltage source. I'll give current source as an exercise for you. Let us say it's Vn M2. Okay. So again, the exercise is same as before. You find the short circuit, current, and then you find the gain from the input to the input here to the output current. Divide the path spectral density by the gain, you get the input referred quantity. So now tell me, if I ignore R naught of all transistors, if I apply small signal voltage at the gate, what is my small signal output current? How much is it? R naught is infinity. For small signals, how will this behave like? Open circuit. Because small signals, this has only R naught. R naught is open circuit. So what is the current? So this is one important property of cascode, that even though you have an additional transistor, if R naught is all infinity, then the cascode transistor does not add any excess noise. Now of course, if you consider R naught, it will be not exactly 0. You'll have some term like 1 by 1 plus some Gm R naught or something. So it will be suppressed by this factor 1 by 1 plus Gm R. So again, I'll give it as a practice problem for you to work out and find what is this factor. And the same, you will be able to get the same result even if you model the noise here using a current source for this transistor. That also I'll give it as a exercise for you to do. So that's one nice thing about cascode. So cascode is like a nice friend who comes and improves the nice properties in your life without making too much of noise. So here, this basically improves the output resistance but adds very little noise. So I'll say okay, cool. So any questions on this? Okay, cool. So now basic noise calculations, hopefully you are comfortable. So let's try to look at our op-amp topologies and see what will be the noise in our op-amps. So let's start with the first candidate. What was the first op-amp topology we saw? The 5 transistor OTA. So let's do that. So let me draw this. So PMOS, NMOS, then we have this. Again, we are looking at small signal. So small signal, this is ground. Let me label transistors. So M0, M1, M2, M3 and M4. Again, remember the equivalent block diagram is this. So we are trying to model the noise in the circuit using an input referred quantity. And first of all, what is the input impedance of the circuit? So what do we need for modeling the noise? Only voltage is sufficient. So, but remember we have two inputs. So you can either say that I model the noise using voltage source at the positive side, or I will say voltage source is added at the negative side, or I can say positive half on this side, negative half on this side. But the final idea is, as a differential input, we are having an input referred noise. That's the point. So we are only finding the effective differential input referred noise voltage. So again, for finding the input referred noise voltage, what will I do for RS? RS is 0, so which means the inputs are shorted here. Because remember, ideally you have an RS and then the small signal voltage V1, V2. For finding the noise, we are making the small signal input voltage is 0, V1, V2 0, and RS is also 0, so that essentially is a short circuit. Great. So exercise is same. How many noise sources are here? 5 are there. So you find the noise from each of these 5 transistors to the output. So again, here short circuit current is easy. You find the output path spectral density in the current, and then what you do? You find the gain from the differential input to the current here. What is the small signal gain from the differential input here to the output current? GM of which transistor? So the gain is already known. The gain is basically GM1 or GM2, doesn't matter. So I just have to find the noise current at the output due to all 5 transistors. Once I do that, I can divide it by GM square and get the input referred path spectral density. Okay. So let's quickly do that. It's actually easy. So let me do it this way. So let me write for all transistors M0, M1, M2, M3, M4. So first I'll find the current I out, and then to find Vn in, this is basically I out by GM1. Correct? So is there some transistor for which we can write the result directly here? M1 and M2, because they are directly at the input. Their input referred noise we can model as an equivalent voltage sources here. So they directly contribute to your overall input referred noise. So M1, M2 we can directly write. That will be Vn1 and Vn2, having a path spectral density of 4 kT gamma by GM1. Here also 4 kT gamma by GM2, but both of them are equal, so I'll say it's GM1. So this way, for M1, M2 we don't have to worry so much. Is okay? So let's now do for the other three transistors. Let's start with M0. Let us say I model this noise using a current source IN0. So I'm injecting a noise current here. Do you think all the current will flow through the output, or what will happen? Let's again ignore R0 for all transistors. No, drain voltages need not be same. This is shorted. What is the impedance looking to the left side? 1 by GM, because I ignored the R0. What about the resistance here? So what will happen to the current? It will split equally. So which means I'll have, let me remove the impedances. I think that's clear for you. I have IN0 by 2 flowing this side, IN0 by 2 flowing this side. which means the current flowing through the PMOS transistor is how much? So what will be the current flowing through the transistor M4 then? Same current mirrors. So I have a current IN0 by 2 here, IN0 by 2 here. What is the current flowing here? So I out is 0. This will also be. Again, this exactly is 0 because I've ignored R0 for all transistors. Again, it should not be surprising because remember that if this is an open circuit, what can you say about the common mode gain of the circuit? Huh? If this is open circuited, if I apply any common mode excitation, what will happen? 0, infinity. 0, why 0? Okay. So let us say I'm trying to find the common mode behavior. So which means equal voltages on both sides. So how do you simplify the circuit now? You can basically short them. So now if this is open circuited, what will be the current flowing? So the output will be 0, right? So here once again you see you have a similar thing happening. You have a common mode excitation injected onto the common node because this has an infinite common mode rejection. This noise current source will not appear at the output. But if that is not clear, at least this expression should be clear, right? Half the current flows here, half the current flows here. Because these two currents are equal, the output current is 0. Cool. So now let's do for M3, M4. That will wrap up. For M3, I can again model the noise as IN3. Okay. Now again R0 is infinity. So what is the resistance looking down? Infinite. So what will happen to this current? Where will it flow? It will flow up or down? Up, right? So which means for simplicity I'll say this is open circuited. So we have the entire current flowing through M3. So what can you say about the current flowing through M4? Same. So this will also be. So what is I out in terms of IN3? Minus IN3. Very good. So this is minus IN3. So when you refer it to the input, it's minus IN3 by G. Is that okay? Now that leaves us with only one last thing. Let's do for M4. Again for M4, I can assume that I have a current source like this. Or let's say push it this way. I'll assume the direction this way. So now tell me how much of IN4 flows to the output. And their current will flow there. So this will directly add here. Plus IN4. This is plus IN4 by G. So that's all. So here we can directly write the part spectral density. I'll write it for the sake of completeness. But till now what I have calculated, is it fine? Any confusions on that? Again, remember these are all small signal calculations. So as long as you are comfortable with that, this should be easy to do. So let's quickly write the overall input referred part spectral density. So I have these two getting added. So I have 8 kT gamma by GM1. What is the part spectral density of this term? For IN3 it is 4 kT gamma times GM3. So this becomes by GM1 square. Same for this. M3 and M4 have the same GM. So this becomes, thank you. So if I were to write it for the sake of completeness, it will look like this: 8 kT gamma by GM plus 8 kT gamma by GM1, or I'll say by GM3 into GM3 by GM1 whole square. Both are same. So the input referred noise voltage of the transistors M1, M2 add directly. For M3, M4 that gets scaled by this factor. Okay. So this directly should tell you something. If I want to reduce the input referred noise, what should I do to GM of the differential pair? Reduce or increase? Increase. Right. And what can you say about the factor GM3 by GM1? That should reduce. So if I'm increasing GM1, do you think my power consumption is increasing or reducing? If I'm increasing GM, power is increasing or reducing? Reducing, remaining constant. Huh? Increases? Is that okay? Confident? So which means my current is increasing, which means I can say that I am basically increasing the power. And this is something we'll see in the next week, that one trade-off with design is if you want to reduce the noise, one trivial choice is to go and increase the power. Right? This we'll see more elaborately, but you can make the inference here. Right? So to reduce noise, these are the things you have to do. So this is SVN of F, right? So okay. Cool. So now we have looked at the noise. It turns out even offset can be easily analyzed in the same framework. That will just take a couple of minutes, so as we'll see. So remember, we already know that transistors will have mismatch, and threshold voltage mismatch is the dominant factor. And the way to model threshold voltage mismatches, you assume that the mismatch in the threshold voltage is added as a small signal voltage at one of the gates. Right? That's all. So which means even if you take your 5 transistor OTA, ideally assume that these two are matched and these two are matched. Because of mismatches in these transistors, threshold voltage mismatches, you will have offset in the circuit. That is ideally, again, this is something we saw in the last class. So ideally your characteristic should look like this, but because of threshold voltage mismatches or any mismatch, you will have shifted characteristic. This is offset. And just like for noise, how we wanted to model the noise as an input referred quantity, similarly for offset also, that's what is preferred. The idea is you assume that the transistors inside are matched, but the overall offset is because of a hypothetical voltage source. That is the input referred offset voltage. Again, finding input referred offset, same principles. You take your circuit with offset, short the input, find for example what is the short circuit current. Ideally, if they are matched with zero input, you should get zero output. If there is a mismatch, even if there is zero input, you get a non-zero output. Now all I need to do is refer this current back to the input. So what will I do to get VOS in? In terms of IOT, what is my VOS in if this has a transconductance GM? By same thing we did for noise. You consider the mismatches in the transistor, make the input 0, find what is the current, divided by the gain from the input voltage to the output current. That gives the input referred offset. Right? That can do it in just one shot easily for this. So let's do that here. So here I'll have mismatch due to what all transistors? M1, M2 and M3, M4. Only two sources we have to consider. There are only two sources of mismatch here. Mismatches in the differential pair, mismatch in the current source. So once again, remember, let us say I'll write it here. So M1, M2. So threshold voltage mismatch in this, how do we model it as? A voltage source at the gate. So once again, from the same understanding from noise, what can you say about the overall input referred offset? How will this add to the overall input referred offset? If I call this delta VTH 1, 2. the mismatch, threshold voltage mismatch in the transistors I have modeled as a small signal voltage delta VTH12. My question is, how will this add to the overall input referred offset? Because finally I am interested to do this, right? I'm interested to add voice in. For noise, what happened? Forget about 4kT. If I had an input referred noise for the transistor, how did it add to the overall input referred noise? It just directly got added. So similarly, what do you think will happen for the offset? Same thing will happen. I mean, if it's not clear, okay, you can do it. See, let us say you assume that threshold voltage mismatch is modeled by a voltage source here. Again, polarity doesn't matter. So the differential voltage is delta VTH12. So what will be the short circuit current? If the short circuit GM you know already, so I have delta VTH12. If the differential voltage is delta VTH12, what will be the short circuit current? Times the short circuit GM. What is the short circuit GM here? So to find the input referred offset, what do I do to this quantity? Divided by the gain. I mean, just like how we did for noise. We find the output quantity divided by the appropriate gain. So here the output quantity is delta VTH times GM. You divide it by the gain, you directly get. So just like for noise, how the noise of the input transistors directly got added to the overall expression. Here also, the threshold voltage mismatch for these two transistors will directly get added to your overall input referred offset. So that leaves us only with M3, M4. So let me erase this because this we have accounted for. For M3, M4, same. You assume that you have a delta VTH34 as a voltage. Now remember, this is, let us say, at an operating point. So this is basically a small signal ground, correct? Because what we are basically doing here, there is some operating point voltage to which I am adding a small signal excitation. So the total small signal voltage I get here is delta VTH34. So what is the small signal current flowing this way? If the small signal gate voltage here is delta VTH34, what is the small signal drain current? Direction, I mean plus or minus GM4 times. So we can direct write it is delta VTH34 times GM4. If I refer it back to the input, it's going to be delta VTH34 times GM4 by GM. So which means, again, the total expression will look like this. My input referred offset, let me just write it and wrap up. So this is delta VTH12 plus delta VTH34 times GM3 by GM1. GM3, GM4 both are equal. So which means if I try to find the standard deviation or the variance here, that will basically be sum of the variances of the individual quantities. Just like in noise, right? The overall part spectral density was sum of the individual part spectral densities because they are uncorrelated and have zero mean. By the same argument, these are also random variables. They are also uncorrelated and have zero mean. So their mean squared value or variance here is sum of the individual variances. So as you see, whatever you had for noise happens for offset also. So for noise, we had 8kT gamma GM, the input transistors directly got added. For the other transistor, we had a scaling factor GM3 by GM1. Even for offset, that's what input transistors directly get added. For the other transistors, you have the scaling factor GM3 by GM1 square. So yeah, I'll stop here and then we can continue.